Hi, my name is Tanya Humboldt. I'm in section 12, and in this video I'm going to introduce irrotational and incompressible vector fields. In this example, we want to prove that the vector field G is irrotational but not incompressible, and that the vector field H is not irrotational but incompressible. First, let's define what it means for a vector field to be irrotational or incompressible. A vector field is irrotational if the curl of that vector field is 0. The result of the curl is a vector, meaning you must take the cross product. A vector field is incompressible if the divergence of that vector field is 0. The result of the divergence is only a scalar, so you don't have to take the cross product. So for a vector field to be irrotational, you take the cross product. In general, that looks like this. Curl of F equals I, J, K. Your second row is partial with respect to x, partial with respect to y, and partial with respect to z. The last row is your function p, q, and r. When you multiply it out, your I component is partial with respect to y of r minus partial with respect to z of q, subtracting your j component, partial with respect to x of r minus partial with respect to z of p, and lastly your k component, partial with respect to x of q minus partial with respect to y of p. So when you simplify it, you should get the 0, 0, 0 vector. This means that your vector field is irrotational. For the divergence, which looks like this, divergence of F equals partial with respect to x of p plus the partial with respect to y of q plus the partial with respect to z of r. If your divergence equals the 0 scalar, that means your vector field is incompressible. So let's prove that G is irrotational and not incompressible. So the curl of G equals the matrix I, J, K, partial with respect to x, partial with respect to y, and partial with respect to z. Your function is 1, y squared, 0. Multiplying that out, your I component is partial with respect to y of 0 minus partial with respect to z of y squared. Subtracting your j component, you get partial with respect to x of 0 minus partial with respect to z of 1. And lastly, your k component is partial with respect to x of y squared minus partial with respect to y of 1. When you simplify it, for the I component, partial with respect to y of 0 is 0, minus partial with respect to z of y squared is 0. So 0 minus 0 is 0. Partial with respect to x of 0 minus partial with respect to z of 1 is 0. 0 minus 0 is 0. And lastly, partial with respect to x of y squared is 0, minus partial with respect to y of 1 is also 0. So G is irrotational. Now for the divergence of G equals partial with respect to x of 1 plus partial with respect to y of y squared plus partial with respect to z of 0. So partial with respect to x of 1 is 0. Partial with respect to y of y squared is 2y. And partial with respect to z of 0 is 0. So 0 plus 2y plus 0 equals 2y. Therefore, it does not equal 0, and it is not incompressible. For h, we want to prove that it is not irrotational and incompressible. So we do the same process with h. So the cross product for h is the curl equals I, j, and k, partial with respect to x, partial with respect to y, partial with respect to z, of the function y cubed, 3, and x. For the I component, you get partial with respect to y of x, minus partial with respect to z of 3, minus your j component, minus. Your j component is partial with respect to x of x, minus partial with respect to z of y cubed, and your k component, partial with respect to x of 3, minus the partial with respect to y of y cubed, when you simplify it, partial with respect to y of x is 0, minus partial with respect to z of 3, 0 minus 0 is 0. Partial with respect to x of x is 1, minus partial with respect to z of y cubed is 0, so here is a negative. So 1 minus 0 is 1, so negative 1. And partial with respect to x of 3 is 0. Partial with respect to y of y cubed is 3y squared, so 0 minus 3y squared is negative 3y squared. This does not equal 0, 0, 0, and it is not irrotational. Lastly, we want to find if it is incompressible. So the divergence of h equals partial with respect to x of y cubed plus partial with respect to y of 3 plus partial with respect to z of x. When you simplify, you get partial with respect to x of y cubed, that's 0. Partial with respect to y of 3 is 0. And partial with respect to z of x is 0. So this equals 0, therefore h is incompressible. So all we've done in this video is define what it means for a vector field to be irrotational or incompressible, prove that G is irrotational and not incompressible, and prove that H is not irrotational but incompressible.